This exercise is to do with the application of the input and output impedance theorem. We've done some exercises involving this double-stage amplifier, the common emitter and the emitter follower. And we've calculated the input and output impedances, mid-band, and in the presence of the C2 bypass capacitor. And the last thing we did was apply the theorem to the coupling capacitors C1 and C3, of which the first step is to put those capacitors into the model. So what we did finally was insert those capacitors and ignore the C2, again assuming that's a complete short circuit. And we discussed how to modify the gain expression to account for the C1 and the C3, which we did by using the extra element theorem in succession. First we put in the C1 and found that it had an inverted pole at omega 3 and no zero that goes with it. Then we did the same thing to put the C3 in. That also has an inverted pole and no zero with it. And the result was this. Here's the mid-band gain, and here's the inverted pole from the first coupling capacitor. Here's the inverted pole from the second one. And as you remember, we were able to use the extra element theorem twice in succession because there was no interaction between the two capacitors in this case. So we get two separate factors, and it's just as though we put them in together or separately or in the reverse order. It wouldn't make any difference. So the gain function now looks like this. And the remaining part of the exercise was to determine the input and output impedances. So here we have the capacitors in place now, and we want to apply the impedance formulas. So here's the solution. The outside output impedance is found by applying the output impedance theorem to the modified gain function in the presence of the two inverted poles, omega 3 and omega 5. And once again, you can take these limits factor by factor. And we've already done the mid-band part of it, so we don't have to do it over again. We can just put in the same answer as before. Namely, we get a mid-band output resistance ROM prime. And all we have to do is work on the remaining factors. And the first thing we do is look into the two corner frequencies and see if RL is contained inside them. And when you look inside the omega 3, you find there is no RL in it. So the omega 3 corner will cancel out from the two positions where A exists. So you don't even need to write it. Previously I've been writing it in and then putting a line through it to cancel it. But now when you get used to that idea, you don't have to write it in the first place. You just leave it out. When you look at omega 5, you find it does have RL in it. So it will be affected by the limit, and it won't cancel out, and so you have to retain it. All that happens is you define a new corner frequency. This factor from the bottom comes around on top, and it simply is a new corner frequency obtained from the old one by letting RL go to 0. And that's the result, automatically in factored pole 0 form. That's for the outside output impedance. If you want the inside output impedance, you take the other limit in the result. So you simply let RL go to infinity in what you have already. So that converts ROM prime to ROM. We've already done it before. You don't have to do it again. You look at the corner frequency in the numerator. It's already had RL limited out of it, so it doesn't change anymore. And the only one that does change is the omega 5 in the denominator, because it still has RL in it. So when you let RL go to infinity in that, the omega 5 goes to 0. So that's an extreme case. So the corner frequency in the denominator simply goes away when you take the limit RL infinite. So what you're left with for the inside output impedance is the flat value ROM at mid-band, and as you go to lower frequencies, it has an inverted 0. That's consistent with what you would expect, of course, simply by looking at the original circuit. This is the model we're working on. If you look back in at the output, for the inside output impedance, that is to the left of the RL, what you're going to look at high frequencies when the cap is a short is the original mid-band value of the inside output resistance. And at lower frequencies, as the cap opens up, all that happens is you get the capacitor in series with that mid-band value, so the output impedance goes up, which is exactly what is predicted from this result. At high frequencies, the output impedance is the flat mid-band value, and at lower frequencies it will rise according to the inverted zero. So that completes the output impedance. To find the input impedance, you simply apply the formula to the appropriate gain, which is now also includes the omega-3 and the omega-5 inverted poles. The mid-band value you don't have to do again. You look at the poles and see where the RS is. This time the RS is absent from the omega-5, so the entire factor cancels, and I haven't shown that before either. You look at the other corner frequency, it does have RS in it, so you're going to have to keep it. And the bottom one comes around on top, unchanged. And when you look at omega-3, as RS goes to infinity, it goes to 0. So the entire corner goes away, and you're left with a mid-band value together with an inverted 0. And if you want the inside input impedance, you take the other limit in the answer, which converts the mid-band value outside to the mid-band value inside, and you look at the remaining corner frequency, and it still has RS in it. So when you let RS go to 0, you change its value, and you get a new one. So you get a new value of inverted 0. So the conclusion is the inside and outside input impedances both have the mid-band values, which are different, and they both have inverted zeros. And that's consistent with looking at the original diagram also, because the inside input impedance is the mid-band value when the cap is a short, and at lower frequencies the cap starts to open up, and so the input impedance will rise. And the same thing will happen for the outside input impedance. The only difference is the mid-band value is larger. But when the cap opens up at low frequencies, again the outside input impedance will take off and start to rise. So that completes the example of applying the input and output impedance theorem to this particular example.